Hey guys, welcome back to part 2 of the video about the universe, all about the universe. If you didn't see the first one, that's okay. It's just continuing on from other articles that I was reading, but I will link to that one in the description if you're interested. If you like this one, you might want to check it out as well. So, we'll get right into it. So the first article I have for you guys is called Why the Big Bang May Not Have Been the Beginning of the Universe. As a child, my fascination with theoretical cosmology was sparked by watching the documentary A Brief History of Time, which delved into the enigma surrounding the Big Bang. The film illustrated how our equations describing space-time collapse into a singularity when we trace time back to the beginning. This raised profound questions about the origins and history of space-time, framing the ultimate cosmological narrative. When the documentary premiered in 1991, the term Big Bang was commonly used in popular science to describe the moment our universe came into existence. This moment marked the inception of time and space, and thus the creation of space-time. This concept wasn't difficult to grasp on a basic level. For instance, my Jewish family's traditional story of the universe's origin bears a striking resemblance to this idea. Fast forward to today, as a physics professor, my understanding of the Big Bang has evolved significantly from what it was in the early 90s. One might assume this change is due to my extensive training in physics, including rigorous postgraduate exams on general relativity and quantum field theory in relativistic spacetimes. While this is partly true, another crucial factor is that the physics community's perspective on the Big Bang has undergone a transformation over the past 3 decades. The Big Bang is no longer necessarily considered the absolute beginning. In fact, there might not have been a traditional beginning at all. 2 major shifts have occurred in how physicists view this cosmological timeline. Firstly, research on inflationary models, which explore the exponential expansion of space-time, suggests that inflation could be an eternal process. This implies that the universe may not have had a specific starting moment and could be eternally inflating even before what we refer to as the Big Bang. If inflationary theory holds, this scenario is the most plausible. Secondly, the term hot Big Bang is now often used to describe a period rather than a singular moment. In the early stages of what we consider our visible universe, space-time was extremely hot and dense. This hot Big Bang era was a chaotic state filled with an energetic substance from which atoms eventually formed, leading to the creation of stars, galaxies, planets, and ultimately life. Recently, a reader pointed out the decline in the popularity of Big Bang articles. While I can't explain the editorial decisions of various publications, I can attest that there's growing consensus in the cosmology community about the inflationary universe. This model, supported by a wealth of data, favors an eternal inflation scenario. Despite this, there are notable critics. Paul Steinhardt, an early proponent of inflation, has become one of its staunchest opponents. He advocates for a competing model of the universe, suggesting a big bounce and a cyclic universe instead of a singular Big Bang. The main issue for physicists is that singularities are problematic, and there's an ongoing search for more satisfying models. Although the concept of a beginning moment aligns with many religious traditions, from a scientific standpoint, a singularity is a mathematical issue needing resolution. Testing models of the very early universe is challenging, but researchers persist. For example, the hypothesis of an eternally inflating universe implies our space-time bubble is just one of many. Astrophysicist Irania Perez and her colleagues have proposed using cosmic microwave background (CMB) data to test for interactions between our space-time bubble and others. The lack of new, sensational ideas might explain the reduced coverage of this topic in popular media. Nonetheless, the question of whether there was a beginning remains endlessly fascinating. Yeah. Well, like, what was there before the Big Bang? There must be some space already existing before. So a lot of people struggle with the idea of it really making sense, So the next article, guys, is called, "Is there an ancient black hole at the edge of the solar system?" Beyond the massive planets of our solar system's outer regions lies a vast and largely uncharted expanse. Astronomers generally believe this area is filled with numerous small, icy bodies akin to Pluto. Several dedicated teams have been scouring this region to uncover these dwarf planets. During their search, some have hypothesized the existence of a much larger object, a planet several times more massive than Earth. This theoretical planet, dubbed Planet 9, is believed to reveal its existence through the gravitational influence it exerts on the orbits of surrounding icy bodies. However, the formation of such a massive planet so far from the Sun presents a significant challenge. All we know is that there's an object of a certain mass out there, says Jacob Schultz, a theorist at Durham University in the UK. The current observations do not provide enough information to definitively identify this object. So if it's not a planet, what could it be? Schultz suggests it might be something even more exotic, a primordial black hole formed during the Big Bang. If proven true, this discovery would be groundbreaking. Primordial black holes could offer a unique window into the early universe and might even comprise dark matter, the elusive substance that binds galaxies together. Cosmologists have long been searching for primordial black holes, but none expected to find one in our own solar system. The pressing question now is how to determine the true nature of the mysterious gravitational source at the solar system's edge. Black holes are regions where space-time is so severely warped that nothing, not even light, can escape their gravitational pull. Predicted by Einstein's general theory of relativity in 1915, black holes were directly detected a century later by the Laser Interferometer Gravitational Wave Observatory, LIGO, which identified gravitational waves from the collision and merger of two black holes. Since then, LIGO has detected about 50 more such events, many of which were unexpected. Previously, black holes were thought to exist in two main categories. The largest are supermassive black holes at the centers of galaxies, including our own, which grow by merging with other black holes and can be millions or billions of times the mass of the Sun. The smaller ones, stellar black holes, form from the explosive deaths of massive stars and typically weigh between 5 and 15 times the mass of the Sun. The 2015 LIGO discovery involved black holes with masses around 35 and 30 times that of the Sun, which was surprising. Subsequent detections revealed more unexpected masses, such as the GW 190814 event, which involved black holes of 23 and 2.6 solar masses. and GW 190521, involving black holes of 85 and 66 solar masses. These observations are very hard to explain with astrophysical scenarios, and they are quite easily explained with primordial black holes, says Sebastian Kless, a cosmologist at the University of Brussels in Belgium. Primordial black holes are thought to form across a wide range of masses, including those as small as planets and asteroids. Theoretically, they emerged from the early universe's dense and energetic environment, collapsing into black holes based on the conditions at the time. Thus, a variety of primordial black hole sizes should exist. While it might seem a stretch to consider Planet 9 as one of these black holes, given its relatively small mass compared to those detected by LIGO, it's a possibility. Estimates suggest that the gravitational source beyond Pluto has a mass between 5 and 15 times that of Earth. This hypothesis gained traction as Schultz and his colleague James Unwin at the University of Illinois pondered the formation scenarios of Planet 9 and found them problematic. The traditional formation process for planets in the solar system involves the coalescence of material in a disk around the Sun. However, this material becomes sparse further from the Sun, making the formation of a large planet like Planet 9 highly unlikely at such a distance. One alternative is that Planet 9 formed closer to the Sun and was later ejected by Jupiter or Saturn's gravity. However, this scenario requires a series of interactions to prevent the planet from returning, which seems overly coincidental. What drew me to the possibility that the mysterious mass at the edge of the solar system could instead be a primordial black hole was another intriguing observation from astronomers looking much further afield, says Schultz. The optical gravitational lensing experiment in Chile, which monitored stars for brightness changes caused by gravitational microlensing, detected several ultra-short events. These could be explained by primordial black holes of a few Earth masses. Schultz noticed a curious alignment. The mini-worlds in the outer solar system suggested a mass similar to those behind the short microlensing events detected by OGLE, the optical gravitational lensing experiment. This hinted at a population of unseen celestial objects that could be primordial black holes. In 2019, Schultz and Unwin published a paper titled "What if Planet 9 is a primordial black hole?", proposing that such a black hole, about the size of a grapefruit, could exist at the solar system's edge. Capturing a free-floating planet from another solar system is improbable, but not impossible. Schultz and Unwin's calculations showed that capturing a primordial black hole is equally plausible. Discovering a primordial black hole in our solar system would be monumental, potentially solving several of cosmology's biggest mysteries, including the nature of dark matter. Primordial black holes, forming in the universe's first moments, would carry information about that crucial time. While traditional telescopes can't see back that far, primordial black holes could offer insights into events just fractions of a second after the Big Bang, including the electron-tweak transition. To prove the existence of a primordial black hole in our solar system, new search methods are needed. Optical telescopes can't see black holes, but X-ray telescopes might detect the bursts of light produced by matter falling into one. Alternatively, a fleet of small spacecraft could track deviations in their trajectories to pinpoint a massive object. Slava Turishev at NASA's Jet Propulsion Laboratory has suggested using solar sails, which need no fuel and can propel spacecraft by the pressure of sunlight. Such a mission could reach Neptune's orbit in about a year, much faster than conventional methods. While some astronomers remain skeptical about the existence of Planet 9, the Vera C. Rubin Observatory in Chile will soon provide more data, potentially confirming or refuting its existence. Whether it's a planet or a primordial black hole, the search for Planet 9 continues. If we find a planet, it will be a significant discovery. If not, and the gravitational anomaly persists, it might be time to launch solar sails to explore further. That would be kind of cool, wouldn't it? If it was that close, they could research it so much easier than all the other black holes that we hear about. Maybe they could send objects into it just to see what happens. Okay, next article is called, "Is the Universe Conscious? It seems impossible until you do the math." So I did read another one of a similar title in the first video, but that one seemed a lot shorter than this article, so hopefully it's not just repeating what the other one said, but I guess it doesn't really matter, does it? And anyway, it's an interesting topic to discuss. The unreasonable effectiveness of mathematics, a term coined by physicist Eugene Wigner in the 1960s, describes how manipulating numbers can predict natural phenomena with remarkable accuracy. This extends from planetary movements to subatomic behavior and even black hole collisions. Now some wonder if mathematics could unravel the mysteries of consciousness, the ability to contemplate the laws of nature itself. This challenge is monumental. The question of how physical matter gives rise to subjective experience is one of the toughest problems in science. The initial mathematical models attempting to explain consciousness have sparked significant debate and some surprising conclusions. Mathematicians are uncovering findings that may force us to rethink our intuitions, suggesting that inanimate matter, and perhaps even the universe, might possess some form of consciousness. Johann Kleiner, a mathematician at the Munich Center for Mathematical Philosophy, believes this could herald a scientific revolution. I just need to readjust my phone stand. I think it's falling down. That's better. For centuries, philosophers have grappled with the nature of consciousness with little success. In the past 50 years, biologists have linked brain activity to specific experiences known as qualia. However, neuroscience has yet to explain how neurons create sensations like joy or anger. Philosopher David Chalmers termed this the hard problem of consciousness due to its inherently subjective nature. Unlike physical phenomena, consciousness is intangible and difficult to measure. Despite these challenges, mathematics has a history of tackling difficult problems. By translating concepts into formal statements, math can reveal insights that elude ordinary language. This approach might help quantify experiences such as the smell of coffee, a task beyond the reach of plain English, as Kleiner notes. Kleiner and Sean Tull, a mathematician at the University of Oxford, are working on formalizing the mathematics of integrated information theory, IIT, the first substantial mathematical theory of consciousness. That would be interesting to hear more about. Giulio Tononi, a neuroscientist at the University of Wisconsin, developed IIT over a decade ago. The theory suggests that consciousness arises from the way information flows between subsystems within a system. Tononi likened these subsystems to islands connected by information traffic. For consciousness to emerge, this traffic must be complex enough to make the islands interdependent, which can be quantified by a value called phi, that little phi word. If information flow between islands is cut off, phi is 0 and there is no consciousness. However, if disrupting the flow affects the system's output, phi is greater than 0, indicating some degree of consciousness. The higher the phi, the more consciousness the system has. According to IIT's exclusion postulate, a group exhibits consciousness only when its phi is maximal, meaning its consciousness surpasses that of its parts and any larger system it's part of. IIT has gained supporters since its introduction. Daniel Bohr at the University of Cambridge finds it appealing, noting a link between consciousness, intelligence, and information processing. IIT aligns with some neurological observations, such as the impact of damage to the cerebral cortex on consciousness. This region's highly interconnected neurons would have a large phi. In contrast, the cerebellum, with many unconnected neurons, has little effect on conscious experience when damaged, as IIT predicts. However, IIT faces challenges. For example, phi should decrease during sleep or anesthesia, but studies show it can increase or stay the same. Additionally, IIT struggles to explain why information flow results in specific experiences, such as the smell of coffee. Critics, like philosopher John Searle, argue that IIT bypasses the core question of how consciousness arises. Practical difficulties also plague IIT. Calculating phi for a brain with 86 billion neurons would take longer than the universe's age. Even for the 302 neuron brain of nematode worm, the calculation would take 5 times 10 to the power of 79 years on a standard computer. Furthermore, applying IIT to systems like a Reed-Solomon decoding circuit used in CDs and DVDs results in a high phi, suggesting it has more consciousness than a human, which seems absurd. Despite these issues, Kleiner believes the solution lies in refining the mathematics. He and Tull have broken IIT into 3 parts: physical systems that encode information, the spaces of conscious experience, and the repertoires of cause and effect. Their preprint paper outlines a consistent way to apply IIT, potentially leading to better models of consciousness or even new theories. One provocative aspect of IIT is its implication that inanimate matter might be conscious, a notion related to panpsychism, which posits that all matter has some form of consciousness. While this idea is contentious, some argue it offers a plausible approach to solving the hard problem. Hedda Hassel-Merck at Inland Norway University of Applied Sciences suggests that fundamental particles might have simple forms of consciousness that combine to create the complex experiences of humans and animals. Quantum theory adds another layer to this debate. It suggests that consciousness might collapse the wave function, a process that determines definite outcomes from quantum possibilities. This participatory universe concept, proposed by physicist John Wheeler, raises questions about the role of consciousness in the cosmos. skepticism remains about whether mathematics can fully explain consciousness. Phil Maguire, a computer scientist at Maynooth University, argues that the complexity of cognitive processes may defy calculation. Philosopher Susan Schneider doubts that math can capture the felt quality of experience. Philip Goff, a proponent of panpsychism, believes consciousness requires more than mathematical and observational tools. Nevertheless, Kleiner is optimistic. He's developing a mathematical model that incorporates private, ineffable experiences, currently under peer review. He's confident that, combined with experiments and philosophy, mathematics can significantly advance our understanding of consciousness. It's very interesting. I never realized that math was even attempting to answer something like that. The next article is called "Why Are There So Many Rogue Planets and What Do They Look Like?" Estimates indicate that our galaxy might host trillions of rogue planets, which are worlds that drift through space without orbiting a star. Most of these planets are likely to be icy, similar to Pluto, but some may be warm enough to support life. Picture a planet where darkness prevails perpetually. Without a sun, there are no cycles of day or night to mark time, and any moons present would be faint and barely visible. These are the rogue planets, isolated worlds floating in the vast expanse of interstellar space. Rogue planets are not just theoretical, they are believed to be abundant. A 2023 study led by David Bennett at NASA's Goddard Space Flight Center suggests that rogue planets might outnumber stars by as much as 20 to 1, translating to trillions in our galaxy alone. While this figure may seem astonishing, it aligns with our understanding of planetary formation. The idea that rogue planets might outnumber stars isn't surprising, says Gavin Coleman from Queen Mary University of London. Astronomers are captivated by this concept. Lisa Kaltenegger at Cornell University reflects on the vastness. Imagining billions of homeless planets drifting through the galaxy is fascinating. Direct observation of rogue planets isn't possible. Since the first potential rogue planet was identified in 2012, their presence has been inferred through gravitational microlensing, which involves detecting how these planets bend light from distant stars and galaxies. This technique suggests that many rogue planets are roughly the size of Earth. Larger rogue planets could form similarly to stars through the gravitational collapse of gas clouds. However, Earth-sized rogue planets likely originate within solar systems before being ejected. This ejection could result from close encounters with other stars or interaction with other planets in the system, leading one planet to be flung outward. Binary star systems, where two stars orbit each other, are prime candidates for producing rogue planets. Binary systems can easily place planets on paths that eventually lead to their ejection, explains Coleman. The environments on rogue planets could vary widely, mirroring the diversity found among planets orbiting stars. These could range from small rocky worlds to large gas giants and icy exoplanets. Without a host star to provide light, any warmth on rogue planets would need to come from internal sources, likely resulting in frozen surfaces. Potential energy sources include thermal vents similar to those driving cryovolcanism on Pluto, caused by the planet's gradual cooling and contraction. Some rogue planets might be warmer if they possess thick hydrogen atmospheres, which can trap heat. David Stevenson from the California Institute of Technology suggests that with sufficient hydrogen, a rogue planet could maintain surface temperatures comparable to Earth, sustained by radioactive decay within its core. Simulations indicate that some rogue planets might even be habitable. This could occur either in subsurface oceans beneath their icy exteriors, or on their surfaces if a dense hydrogen atmosphere can retain enough heat to support life. That's another interesting topic. All these things I just never knew. I was taking a walk the other night and I looked up at the sky and I could see the Milky Way, like really looking at it, fascinated by it more than I have been in a while, just because I've been reading all of this stuff recently. I guess it gave me a new appreciation for it. Next article, guys, is called "The Galactic Anomalies Hinting Dark Matter is Weirder Than We Thought." Cosmological puzzles are pushing astronomers to reconsider the conventional understanding of the universe, raising the possibility that dark matter is more bizarre than previously believed. The Milky Way might not seem delicate at first glance, but when Mariangela Lisanti, a particle physicist at Princeton University, started experimenting with the components of our galaxy, she found it to be surprisingly fragile. Lisanti's simulations involved altering a small fraction of dark matter, the mysterious substance believed to make up over 80% of the universe's matter, with something more complex. She thought a minor adjustment of 5% would be inconsequential. "We thought we're only adding 5%, everything will be fine," she recalls. "But then we just broke the galaxy." Such tinkering is justified because, since the 1980s, astronomical evidence has suggested that dark matter is a single type of slow-moving particle that doesn't interact with itself. Despite extensive searches by particle physicists, this elusive particle remains undetected, perhaps because dark matter isn't what we have always imagined. Recently, several galactic anomalies have ignited a rush to explore alternative theories. This complex dark matter could range from subatomic particles that interact with each other to families of dark particles forming dark atoms, stars, and even galaxies. The possibilities are vast and daunting. However, new observations of galactic anomalies promise to narrow down these options. With upcoming telescopes, we might soon uncover the true nature of this mysterious substance. Our understanding of the cosmos hinges on dark matter, an idea that first intrigued astronomers in the 1930s. Back then, astronomer Fritz Zwicky proposed that unseen matter was holding galaxy clusters together. This concept was solidified in the 1960s when Vera Rubin demonstrated that galaxies were rotating too quickly to stay intact without some form of invisible matter acting as a gravitational glue. In the 1980s, cosmologist Jim Peebles suggested that dark matter consisted of sluggish, massive particles yet to be discovered. Peebles' cold dark matter, CDM theory, has been crucial to our cosmological model, known as lambda CDM, which posits that the universe consists of ordinary matter, dark energy, and cold dark matter. Cold indicates that dark matter moves slowly and interacts only through gravity. This model aligns well with large-scale observations of the universe, making it a long-standing theory. With cosmology, cold dark matter has held up amazingly well, says Lisanti. On those scales, it's beautiful. Yet, there are problems with cold dark matter. The most glaring issue is the absence of particles matching this description despite decades of searching. The Large Hadron Collider at CERN expected to find supersymmetric particles like the photino, a candidate for cold dark matter, has found none. Furthermore, recent detailed examinations of the universe's structure have revealed anomalies that suggest cold dark matter might not tell the whole story. For instance, the missing satellites problem arises from theories predicting numerous small sub-halos around every galaxy, which should lead to many dwarf galaxies orbiting the Milky Way. However, we observe far fewer than predicted. While it's possible that only the largest halos form satellite galaxies, leaving many dark sub-halos undetected, we still don't see them. These sub-halos should affect star streams, ribbons of stars torn from cannibalized clusters or small galaxies. Yet little evidence supports this interaction. In 2018, Adrian Price-Whelan at Princeton and Anna Bonacca at the Harvard-Smithsonian Center for Astrophysics found gaps in the star stream GD1, suggesting multiple impacts by dark matter subhalos. It's super exciting and intriguing, but it's also still only one, says Lasanti. Moreover, the core cusp problem presents another challenge to the cold dark matter model. Simulations predict that dark matter should be densest at the center of galaxies, but observations show a more uniform distribution, indicating something more complex might be at play. This has led some astronomers to consider complex dark matter models, which include multiple particles and new forces of nature. Complex dark matter models abound. Some propose a mix of cold and warm, faster-moving dark matter, while others suggest self-interacting, decaying, or annihilating dark matter. Testing these models is a formidable task. Each one of these simulations takes 3 or 4 months to run, says Lasanti. Her team, like others, modifies dark matter properties in simulations to see how changes affect galaxy formation. In one experiment, converting just 5% of cold dark matter into complex types prevented the Milky Way's formation, highlighting the sensitivity of our models. This rich variety of behaviors from different dark matter models is both promising and challenging. Allowing dark matter particles to lose energy revealed new possibilities. The dark matter would collapse down, and then we don't really know yet what all the structures are that it can form when it collapses, says Lasanti. Particle physicists are exploring various theories. David Curtin from the University of Toronto has proposed a form of supersymmetry where all matter switches to a twin set of particles with their own forces. These twin particles, which only interact through gravity, would form dark matter capable of creating dark atoms and even dark galaxies. This atomic dark matter could form structures like those we see with normal matter, potentially resulting in an invisible galaxy overlapping the Milky Way. Future telescopes might detect such dark galaxies through microlensing, where the gravitational influence of dark matter would momentarily brighten background stars. Curtin's team suggests the Vera C. Rubin Observatory in Chile could identify these signals when it begins operations next year. Despite these advances, some astronomers like Boylan Kolchin believe it's too soon to dismiss cold dark matter entirely. There are lots of little indications that things are at least not as simple as one might think, he says. But it's not clear there's something more complicated happening in dark matter. Alternative explanations could involve normal matter behaving in unexpected ways. Astronomers focus on gravity, but better modelling of thermodynamic processes, such as supernova explosions, might reveal more complex behaviours. Lisanti and her colleagues will continue their simulations to explore complex dark matter possibilities. While it seems unlikely to replace cold dark matter entirely, the existing model's resilience suggests that minor adjustments might suffice. Perhaps the key lies not in replacing an ingredient, but in adding a bit of seasoning to perfect our cosmic recipe. And guys, I just have one more article for you. Something a little less brainy, but still insightful, I would say. And this one is the best science fiction films about space, according to an astrophysicist. As an astronomer who delves into the ethics of human space settlement, I recently explored these themes in my book, Off Earth: Ethical Questions and Quandaries for Living in Outer Space. My journey into this unique career was deeply influenced by science fiction, a genre that grapples with complex ethical questions alongside its captivating visuals of aliens and space adventures. This list highlights films about space exploration that reflect our society or one quite similar to it, excluding those set in utopian federations or distant galaxies, and those where space comes to Earth. Here are my top 10 picks for the best space movies so far. Number 1 is called Hidden Figures from 2016. Based on Margot Lee Shetterly's excellent non-fiction book, Hidden Figures celebrates the contributions of 3 brilliant black women to the early US space program in the 1960s. The film showcases space exploration as a collective effort, with John Glenn's spaceflight success resting on the shoulders of engineers, mathematicians, and programmers. However, it also highlights the social challenges within the space program, particularly the barriers faced by marginalized workers. Number 2, Apollo 13 from 1995. Apollo 13 recounts the gripping true story of the moon mission gone awry and the extraordinary efforts to safely return its astronauts. The film emphasizes the ingenuity and perseverance of both the ground crew and the astronauts. Director Ron Howard's decision to film realistic weightless scenes using an aircraft performing zero-G maneuvers, rather than relying on 1990s CGI, ensures the movie remains visually compelling even today. Number 3, Gravity from 2013. Gravity is visually stunning and intensely suspenseful, portraying a fictional space accident where the protagonist must manage her own survival. It's a woman versus nature narrative, with nature being the cold, airless void of space. Despite one significant exception, the physics in the film is remarkably realistic, presenting space as a brutal and unforgiving antagonist. Number 4, The Martian, 2015. In The Martian, a botanist astronaut survives alone on Mars using potatoes, fertilizer, and a positive attitude. The film blends the survival aspects of Gravity with the collaborative problem-solving spirit of Apollo 13. It offers a glimpse into how humans might one day live intentionally away from Earth with reasonably realistic Martian survival techniques. Number 5, Moon, 2009. Moon mixes space exploration with additional sci-fi elements, telling the story of a lone lunar miner who discovers his employer's unethical cloning practices to cut costs. While space mining and human cloning are still speculative, the film's depiction of corporate exploitation is chillingly realistic. I don't think I've heard of that one. Number 6, Sunshine from 2007. Sunshine is unique among space movies, focusing on a mission to reignite the dying sun with a massive bomb. The film explores themes of sacrifice, beauty, spirituality, and the potential dangers of obsession with science. It's a story filled with both scientific wonder and dramatic action, appealing to a wide audience. Number 7. Silent Running, 1972. This melancholy film uses space to preserve Earth's last forests after an ecological catastrophe. Silent Running is a cautionary tale about a future where Earth is comfortable for humans but devoid of nature, using space as a sanctuary and a dumping ground for the biosphere. Number 8. WALL-E, 2008. In this animated feature, humanity is relocated to a space cruiser while robots clean up their mess on Earth. WALL-E shares Silent Running's environmental message, but is more optimistic, with humans rediscovering the value of nature through the help of adorable robot friends. Yeah, I liked that one. Number 9. Contact, 1997. Contact follows a radio astronomer who discovers a message from extraterrestrials containing blueprints for a spacecraft. The film is celebrated for its exploration of science versus faith, its awe-inspiring portrayal of the universe, and its protagonist, Ellie Arroway, who has inspired many current astronomers. And number 10, 2001, A Space Odyssey from 1968. This one has profoundly influenced space cinema. The film presents a future in space as both a mundane workplace and a realm of mind-bending phenomena that could change humanity forever. Its legacy is reflected in many subsequent films, making it a cornerstone of the genre. I really love Stanley Kubrick, and I think I tried to watch this movie, and I turned it off maybe after half an hour. And I have heard that it can be a difficult film to watch for some people because it moves so slowly. So I don't know if I'll ever watch it. Because if I put it on when I feel like relaxing, I'd probably just fall asleep. But I can't see myself sitting through 2 hours or whatever. Just this slow-moving movie. But yeah, if you're obsessed with space, you might like it. So guys, that wraps it up for this video. I hope you've enjoyed this. I hope you're asleep right now or feeling really relaxed. And I appreciate you guys tuning in and the thoughts that you guys have that you leave in the comments. I do have another couple of videos that will be all about time coming up that I got from the New Scientist website, and then my subscription expired. But I'll keep doing science videos. Just gonna find more topics to talk about. If you guys have any ideas of things that you want me to ramble on about, let me know. Otherwise, I'm also going to do some videos related to travel, because that's really on my mind right now. I have no plans to travel, but I feel like I'm kind of dying for it. But I have no idea where I would even go. So I'm just planning on looking up different locations and talking a bit about them. So that should be nice. And a nice thing to visualize and imagine, even just for the fun of imagining it. Yeah. And let me know what else you guys have in mind. Until then, I will see you next time.